Thank you, Mahelani, and thank you all for being here this evening. It's a pleasure to come here and give this talk about something that's been in the news quite a bit lately. Is this on? Can you guys hear me? Okay. Speak up a little bit? Okay.
Point it toward you.
So we're going to do like this? Oh, there we go. I need like a boom stand or something, right? So high sea levels have been in the news a lot lately here in Hawaii, and I'm going to talk to you tonight about this in the context of something called clear sky flooding. And that's kind of a new term that we've been throwing around in coastal science. And it's the reason we started using this term is because it's different from when you have a storm nearby. When you have a storm nearby, you have storm surge, you have wind, you have rain, you have all different kinds of things that can lead to flooding in certain areas. But what do you do when there's not a cloud in the sky? It's the best day you've ever seen, and your beaches are flooded, and there's water in the roads, and your roads are flooded. It's a totally different thing, right? And so what we've been trying to do is understand why those types of events happen. And one of the things that they've been talking about a lot on the news are the king tides. This has been a big time buzzword over the past few weeks, and if you're watching the news, you've probably heard a lot about it. And these are just a few screenshots from various news organizations around the state, and you can see that they've had that plastered all over various headlines and things like that. And if you've been paying too close attention, you might have had this guy in your nightmares. It's kind of funny for a couple reasons. One of the reasons it's funny is because I think this is Seattle here in the background. Somehow New York is here in the foreground, right? So I'm not sure how that ocean got between. But more importantly, I think this is kind of indicative of sort of a misconception, I think, in the way that these recent events have been communicated, because this gives the idea that it's the king tides that are coming for us, right? That's what's going to threaten our coastal infrastructure and ecosystems in the coastal zone and that sort of thing. When in reality, and I'm going to try to convince you of this during this talk, it's not really the king tides that are the issue. King tides are sort of a regular phenomenon. They happen every year. But there are a lot of other things going on that we've been having, that have been going on in the Pacific Ocean recently that are actually the culprit here. And we're going to talk about some of those. So with that introduction, some of the things I hope to answer while we go through this. So what exactly is a king tide? Let's define that. It's been thrown around a lot in the news. Let's actually talk about what a king tide is. Is that really a thing? Some people have been asking us at the Sea Level Center, what is king tide? Did you guys make that up? Like, what is that? And then obviously, once we define that, what were the king tides involved in what we observed recently in our coastal environment? And so here are some pictures from the end of April 2017. These two kind of on the bookends here are beaches in Waikiki. You can see the water level up on the sand where you would normally have tourists on their towels and hanging out and enjoying the sun. But there's no room during this period. This is the road between Kaimana and Kapiolani Park. And so you see there's quite a bit of water here on the road, and there's no rain during this time. This isn't rain flooding. This is just from the water level around the island, and I'll tell you about why the waters are elevated here as we go along. So again, I mentioned that king tides are kind of a regular phenomenon, so there has to be something else that's setting this apart, and we'll talk about what else is going on. And then finally, just a little bit about what does this mean for the future. Not only looking way far in advance with a lot of sea level rise coming in the 21st century, but also just for the rest of the summer. So what can we expect for the next few months or so? So some of this might be a little below you guys if you've been in Hawaii for a long time and you're used to thinking about tides and stuff. But I do think in order to understand what a king tide is, we should just start at the beginning, start with the basics really fast, and kind of work through this really simply. So Tides 101 here is that basically it's all about gravity. So you have the simplest kind of thing here is we have Earth and we have the moon, and the moon has a gravitational pull, and it's pulling on the ocean, and it's pulling the ocean away from the Earth, and it's creating a tidal bulge here on one side of the Earth closest to the moon. Now, that seems kind of straightforward. But what's a little less straightforward, there are a couple of ways physically you can think about this, but I think the easiest way to think about this is how, and I'm talking about how we figure out what's going on with this second bulge on the other side of Earth. Why is there a second high tide bulge on the other side? And kind of the simplest physical explanation is to think about it this way. So the moon is pulling the ocean away from the Earth on this side, but the moon is also pulling the Earth away from the ocean on this side. You can think about it that way, or you can think about it in terms of centrifugal force and things like that. But the first way is a much more simple way to think about it. Now, when you have these two bulges, you also have, that water has to come from somewhere, so you have two low tide areas as well. And then the Earth is obviously rotating beneath this shape of the ocean. And so here's Hawaii. You can see it kind of here in the upper left. And so Hawaii is going to be rotating around and hitting the different bulges as it goes around, 2 high tides a day, 2 low tides a day. So everybody kind of knows that, 2 high tides a day, 2 low tides a day. But you also have to add in the fact that the sun is involved here as well. And the sun has a fairly substantial gravitational force as well and impacts our tides. And the moon goes around the Earth once every about 28 days. So within that 28 days, twice during that time period, the sun, the moon, and the Earth are in a straight line. When those three things are in a straight line, we have higher than normal high tides. We call that spring tides. Higher than normal high tides and lower than normal low tides. So the tidal range is bigger. Then there are 2 times per month when you have the Earth, the moon, and the sun sort of at a right angle to each other. And at that point in time, the gravitational forces are kind of canceling each other a little bit. And when they cancel, you get lower than normal high tides, and your low tides are not as low. So you have a smaller tidal range, right? So this is the spring neap cycle. Spring tides when everything's in line, neap tides when things are at right angles. So 2 high tides per day, 2 times per month when you have higher than normal high tides. Okay, so that's the kind of basics. I think everybody probably is used to thinking about those 2 things. But let's go on to what is a king tide. And to get at this, everything in nature and in science always has another level of complexity. And the next level of complexity for the Earth is the shape of the orbits and the inclination of the orbits. Actually, I think I messed this up. This should be the inclination of Earth's axis here. There are certain times of the year when Earth is closer to the sun. So the Earth's orbit is elliptical, and the sun is not necessarily at the center of that orbit. So there are certain times of year, namely during northern hemisphere winter, when the sun is closer to where the Earth is closer to the sun. So that also increases the tidal amplitude during that time. In addition, we also have the Earth tilted on an axis, and there are certain times of the year when the tilt of that axis, as it stays in the same orientation, but so it's tilted towards the Earth during summer and away from the Earth during winter as it goes around. And so there are certain ways in which the sun and the moon can align during summer that actually give us higher tides than normal during the summer. So we have 2 periods during the year, during winter and during summer, when the spring tides are higher than normal. It happens about 2 to 3 times a year, and those are the king tides. So the king tides, like I said, they happen every year. They're only due to astronomical forcing. They're only due to the configuration and the orientation of the sun, the moon, and the Earth. That is a king tide. They happen every year. So then the question becomes, if king tides are happening every year, then what is actually going on right now? And why are we actually having the higher than normal sea levels? Why didn't we have this before? Why haven't we seen this in previous years? So to answer that question, what I want to do is go to our Honolulu tide gauge and look at some data. So we have, fortunately here in Hawaii, so this is actually a building out on Pier 4 on Sand Island. It's a small structure, and inside the structure are some instruments that go down below into the water, and they're measuring the water level. And we've had a tide gauge in Honolulu Harbor since the early 20th century. It's one of the longest and highest quality records in the entire world. And so what we can do is use that to kind of piece apart the different types of processes that are going on in the ocean, what changes water level at our coastlines. And we're going to try to piece this apart here and kind of use it like an onion. We're going to pull off the layers, and we're going to associate each layer with a different type of coastal process or oceanographic process. So this is the actual record. So you can see it starts here at 1905, going all the way to present. And these are hourly sea levels from Honolulu Harbor. You see, it's really an awesome record, but there are a couple of things that really stand out when you look at this. First of all, there's a pretty huge range here. I mean, we're talking about -1 to up to 3 feet, you know, going back and forth. So a pretty large range in the water level. It's also a fairly clear trend, and we'll pick this out a little more clearly here in a bit. But there's a pretty clear trend here. And you can convince yourself of that by looking at this kind of 3-foot water line here. Look at that. And then look at about 1970. There are no hourly values that exceed that line. After about 1970, you can see that there are quite a few. And the number increases. We have quite a few in the most recent decades. And if you look here, the most recent time period, that's where we are now. And so we have some pretty high sea levels. And what we're going to do is try to get at this, understand why is this high right now. So the first thing we can do is to do some data analysis, I don't want to call them tricks, but techniques, to separate out what is tide, what is due to the sun, earth, and moon, and what's due to everything else. So that's what I've done here. So this is the tide part in blue, and the orange part here is everything else, but I've also taken a daily average there just to kind of scale it down a bit so that we can see both. And so one way you can think about this is that in terms of sea level, the blue here is astronomy. That's Earth, Moon, and Sun, and the gravity between them and how they orbit each other. And the orange is climate and oceanography. So we've kind of separated these two things out here. We have tides and we have everything else, which is really what's going on in the ocean and climate system. Okay, so I'm going to start with the tide part of this. I'm going to start with the tide part of this, and we're going to focus in on just the most recent year here. So now I've taken the tide part from that blue curve from the last figure, and I've plotted just the last year, but I've also only taken the highest point every day. So this is the highest tidal height every single day for the last year. And immediately you can see a couple of things we've already talked about. One, the spring and neap cycle. So over about a month, you have the highest high tide, a slightly lower high tide, or slightly lower, and then high. And so you can see this, or I'm sorry, high, low, high, low, high. So that's the spring neap cycle. And then, in addition to that, like we said before, there are certain times of the year when the high tides are higher. Yeah. So, and we said that would be in winter and summer. So here is during the winter. We have the highest high tides of the past year during winter. We have the highest and the second highest high tides of the past year during summer here. So I didn't explain this axis very well, but this is summer 2016, July 2016, and going through to November 2016, and then January 2017. So this is the winter, summer. So those are those annual variations in the tides that we're talking about. And here, this is April 30th when we had the flooding. So it doesn't look that impressive in the tide, really, does it? I mean, I would say it's higher than normal, but it's definitely not extraordinary. Yeah, but keep in mind, this is only the tide part. This is the astronomy part. This is the Earth, Sun, Moon part of this puzzle. So that it's contributing, I would say, to the high water levels that we saw and the flooding in our streets, but it's definitely not the whole story. And so when we talk about king tide this, king tide that, that's really not the whole story. It's part of it, but it's not the whole story. Okay, so this is kind of the same deal. I just wanted to show the same exact thing. So this is now for the last 20 years, and I've taken the highest daily tide from the last 20 years. And so now you can see, so now you're seeing kind of the year to year. So probably what would this be? Summer, winter, summer, winter, summer, winter kind of thing. And here is April 30th. You can see that it's certainly not extraordinary in terms of the tide over the past 20 years. There's been many other things, or many other tides that are higher. And so if the tides were the only thing going on, we would expect to see similar types of flooding during those times. Okay, so yeah, so that's basically what I just said. So that's not the only thing going on. So let's try to figure out what else may have contributed. Okay, so I'm going to go back a few slides, and I'm just going to go back to this. Remember, we separated this into tides, and we separated it into everything else, which we called climate and oceanography. So now let's just focus on that climate and oceanography part. That is this now, and now it's in its own plot. This is the climate and oceanography part. So this is with the tides taken out, and going all the way back to 1905, and this is April 30th. So April 30th, in terms of the oceanography and climate part, when you take the tides out, it was the highest daily average sea level we've ever recorded in Honolulu. It was April 30th, 2017. And when you start to ask yourself why that might be, there's a couple of different reasons. You can kind of pick this out a little bit with your eyes. So first of all, there's a pretty clear trend. Yeah, so a pretty clear linear trend going from early 1900s to present. But this alone would not set a record, just having a trend. So this value out here, just a trend alone, is not going to set the record. You also have to have some short-term fluctuations as well. So you see this kind of short-term fluctuation here on the end, but there are similar short-term fluctuations relative to this trend line that are pretty much just as large, right? So you have to have both. You have to have the trend line and you have to have a short-term fluctuation, both of them together, to create this record high sea level that we had at the end of the end of April. Okay, so yeah, right. So that we talked about the trend, and now I'm going to talk a little bit about the short-term fluctuation there on the end and what might be causing that, because that's kind of the most interesting part here. So now I'm blowing this up again, and now I'm showing that same climate and oceanography part of the time series from 2010 to present. And again, here's April 30th. You see it poking out way up there. And there's a couple of things here, and again, you kind of get the same sense, right? It's sort of like you have an upward trend here, kind of from 2015 and on. And then we also have a short-term fluctuation here at the very end. So now we have a trend, which is sea level rise. And on top of that, we have a slow ramp up from about 2014, 2015 to now. And we also have a spike at the end of April. So all three of those things together are giving us the high sea level that we observed. So I'm going to start with the slow ramp up, the one from 2014 to present. And I'm going to talk about in the context of wind and sea level in the Pacific Ocean. So typically, typically the trade winds are blowing from east to west. And what happens is this water at the surface, this warm water at the surface that gets heated by the sun, it gets driven to the west and pushed to the west. When you push that water to the west, it has to be replaced with colder water from below, right? So what you end up doing is piling up warm water in the east and upwelling cool water in the piling up warm water in the west, bringing cool water up from depth in the east. And so on average, we have warmer water in the west, which is less dense, has more volume, and sits higher. So there's higher sea level in the west and lower sea level in the east where the water is cooler. So on average, we have this difference from west to east of high sea level in the west and low sea level in the east. So what happens when the trade winds stop? Does anybody know what that's called? El Nino. So when we have an El Nino, what happens is the trade winds relax. And so that gradient, or that difference from west to east of high sea level here, low sea level here, it evens out. But what's really interesting about the ocean and the fact that we're on a rotating sphere is that the ocean rarely behaves like you would think it would. The fact of the matter is that when that sea level evens out, it doesn't just even out equally in all directions at the same time. What happens, and I'll show you this in some data here, is that the pathway of that warm water that started here and spreads out, it actually goes east along the equator first, as maybe you might expect. But then it turns north along North America, and then it goes west toward Hawaii after that. And so I'm going to try to show you how that works here. And what I've done here is taking, these are maps of sea level from satellites. So satellites measuring sea level from space. And the color, and these are in 3 month bins. So this is an average from October to December of 2015. Now we have January to March 2016. And then onward until the end, we have the first 3 months of 2017 here in the final. Okay. Now the colors here are, blue is for lower than normal, and red is for higher than normal, okay? So what we've seen here is this is when the peak of the El Nino was. So this would have been when the trade winds got the weakest. And so what happens was that high sea level was here, dropped, right? So this is lower than normal. Sea level over here rises because it's higher than normal, so this is starting to spread out. It spreads out to the east, and this happens fairly quickly. You can follow with your eye the sea level spreading northward now along the North American coast. Yep. And then once it gets there, then it starts to separate and it propagates back west out into the basin. And again, the weirdness of Earth being a rotating sphere, when it starts to go west, it happens faster at south of Hawaii, and it happens slower and slower the further north you go. So you can see once it hits the eastern boundary here, it races out kind of at low latitudes here, but then it happens a little slower up here. So it's racing out, but it's just now starting to sort of get around to Hawaii here. This is kind of gone now, but we're just kind of hitting the peak here in Hawaii, and then, or I guess here would really be the peak, where the sea level is just kind of finally making it over to Hawaii. And that is the remnants of the 2015-2016 El Nino that happened a year and a half ago. And we're seeing the sea level now, which I think is pretty cool. So, so that's part of the story, and that is what accounts for. That is what accounts for this slow ramp up. It's the end of the El Nino, and the sea level and the warm water propagating around the basin and hitting us a year and a half later. So now, let's go to the, let's focus now on the short-term spike sort of at the end of the record that gets added on top there. And now I'm going to show you again a little movie, but these are again measurements of sea surface height or sea level from satellites, again from space. And these are now daily maps moving from the end of April to roughly the end of May. And what you see is a lot of really interesting structure here, a lot of what looks like to be cyclonic structure, right? And what these are eddies moving through and around our islands. They're coming from the east and moving through the islands. The red colors here are higher sea level. These are eddies that have warm water at their core, and they spin clockwise. You can't see the spin here because the resolution of the satellite is not, or at least in this product, is not high enough. Excuse me. And the cool core eddies rotate. And those are the cooler colors here. Those have cold sea level or cold water at their cores and low sea level, and they rotate counterclockwise. And so if we wait for this to come around again, and you watch, I think it starts around the last week of April or something like that. Wait for it to come around again, and you'll see, if you get to around April 30th, see that big red sea level eddy kind of peeking around Oahu? There's a couple in the vicinity, but they're all kind of impacting the sea level around Oahu. And so that is kind of the final piece, or at least for the sea level part. So we have a couple of things now, or three things actually, just for the sea level, the oceanography and climate part. We have the sea level rise, which was necessary to get us to that record level, but it wasn't the whole story either. We have the slow ramp up caused by El Nino, also important piece of the story. And then we have eddies going through the islands as well. So there's another little peak on the end. So it's really a confluence of things that have led to that event at the end of April. But there's one final thing also, and that's the wave piece. Right? We haven't talked about waves yet, and so the wave piece here in Hawaii is a little different than you might think if you were living on a sandy beach somewhere in Miami, right? Because here we have very large reefs that fringe our entire island. So that changes things a little bit. And so rarely do we have much wave energy that actually, there are a few places on the island, but very few, where the wave energy actually hits the shoreline. For the most part, the wave energy is out here. Yeah, this is in Waikiki, I'm sure you can recognize. And if you're walking along the beach here, you might see a few little rollers come in and lap on your ankles. But for the most part, that wave energy stays out there. It stays out on the reef. But that doesn't mean that the waves don't affect shoreline and water level. And in fact, the waves, when they break out here, they have there's a couple of ways to think about this as well. But one way is to think of the kinetic energy, or the energy of the motion in that wave breaking, gets converted to potential energy. And that happens because all that momentum in the waves that's coming in, you can feel it when you get hit by one of those waves, right? I mean, there's a lot of momentum. That momentum has to go somewhere. And it gets transferred into the water column, the shallow water over the reef. And what it leads to is that constant breaking of waves out here on the outer reef gets transferred into a general uniform rise of water level along the shoreline. Now you can't really see it here because we're talking about a couple of feet, maybe 3, if on really big swells. But you have, there would be a slow slope up of the water level from the white water here where the waves are breaking up towards the shoreline. That's called wave setup. So that's another piece, kind of the cherry on top of a coastal clear sky flooding event. And so this is kind of like your cartoon model of what's going on here, right? And you can see the wave part. I tried to kind of capture the slow increase of sea level from the breaking waves up to the shoreline. So that would be your wave setup. And then we also have the background piece, which I'm using to talk about all those things we talked about with the oceanography and climate. So that would be your eddies, El Nino, global sea level rise. That's a piece as well. And then all that is on top of the tides. So it's really kind of this like a layer. I mean, obviously in the ocean, there's no water and oil layers like this, but it's all mixed together. But you can think of that as these contributions sort of adding on top of each other to create high water level at the coastline that can cause inundation. So if we kind of piece this all together, when we had this kind of flooding that I showed you at the beginning of the talk, we had a couple of things going on. We had higher than normal, though, like I showed you, not extraordinary tides. We had the delayed response from the El Nino event. We had a high sea level eddy in the vicinity of our island. And we also had what was our first kind of substantial swell of the year. It wasn't a huge swell, but it was a pretty big one. It was the first one, and it happened at the same time. So we had the wave setup piece on top of all those other ones as well. And so the last little thing I'll talk about here just for a few minutes is, how often can we expect these similar types of these events to happen in the future? Yeah?
Is this Waikiki?
Yeah, this is Waikiki. So this is Waikiki Beach here, and this is the road between Kaimana Beach and Kapilani Park. So it's important. Like how often are we going to have to deal with this going forward? Not only in the far term, in the decades in the future, but also just for the rest of the summer. So this is kind of a complicated figure, but it's something that we put together at the Sea Level Center, trying to kind of synthesize a lot of this information. And so this is kind of our best guess of what's going to happen for the rest of the summer, anyway. Okay. So let me walk you through some of this stuff. So this here is the very end, basically, of the tide gauge, the observations from the tide gauge that I just showed you. This is the very end. Here's that record-setting high sea level that we talked about. This is our best guess of what's going to happen over the next 6 months. Now, this was not from a model. This was actually from, so when we looked at those maps from the El Nino event, and also when we looked at the eddies, if you noticed, everything was coming from the east, right? So what we can do is by looking at, by our knowledge of the dynamics of the ocean and how and why and how fast those types of things move towards us, and also by using some statistical techniques as well, we can come up with a best guess of when those various things to the east are going to come our way. So we integrate all those things together. This is our best guess kind of forecast. There's a little bit of an error bar. I don't know how well you can see it there on the screen, but there's a shaded area here that kind of gives an area of how confident we think we are in that forecast going forward. And then on top of that, we also have sort of a similar thing of what I was telling you before. So we know well in advance where the moon, the sun, and the earth are going to be relative to each other. We can predict tides very easily going forward. So we can look at, so this is now the daily maximum water level going for the rest of the summer. So this is not the full tide, this is just the daily maximum tidal level. So when we add this to this, the tides, this is our best guess of how high the water level will be at your shoreline, not including the wave part, going forward for the next 6 months. And already you can see that just mostly from the tides, if you look at the end of June and the end of July, that is when we need to have our heads up. And we also had one similarly, and this is actually was kind of funny because it was getting all the attention, right? So we had this thing that happened in at the end of May or the end of April, beginning of May. And then when it came back around for the end of May, everybody was in a tizzy, and that's when we had all the news stories and everything. But it didn't really pan out, and part of that was because the swell that was predicted didn't really pan out. But we also didn't have a high sea level eddy in the region either. So what we need to do, and the eddies are difficult to predict, and the waves are difficult to predict. That's essentially weather prediction. So what we need to do, though, is have our heads up for these areas. And then if we do see a large swell being predicted, and if we do look at our real-time maps of sea level from satellites, and we see a high eddy in the region, this is when we should be concerned about having some flooding in the roads or having some erosion on our beaches and that sort of thing. So that's kind of a look for the rest of the summer from what we've learned by looking at these types of events.
So does this predictive curve not include the shorter term eddies?
I guess technically they're in there, but they're smoothed. So because they're essentially turbulence in the ocean. So it's very difficult to predict. But yeah, so they're kind of smooth through. Okay, so right. So that's kind of the rest of the summer. Let's take a look at the rest of the 21st century and just get a rough idea of how many times we can expect to see events like the end of April going forward. So what we can do is we can take what we know about these types of events from our really awesome tide gauge record that we have, and we can also look at global climate models going forward for various scenarios of how much greenhouse gas gets emitted into the atmosphere going forward and how much that will change sea level going forward. And we can combine this information with what we know from the past and get an idea of how often we expect to see water levels that high that we saw on April 30th. Okay, so if we look at 2030 based on our analysis, we expect to see days like April 30th about 3 to 4 times per year in about 2030. So that may not seem like a lot, but think about it this way. That was the largest one we'd ever seen before, right? So that was in 100 years, that was the largest sea level value we'd ever seen. By 2030, we expect to see that 3 to 4 times a year. So that's a big change. If we look at 2050, now we're talking about 25 to 40 times every year we get to see that level. And again, these are not catastrophic events, but they're nuisance events, and they add up. And it adds up in not only in the economy with tourists, if they come and they want to hang out on the beach, but there's no beach for them to hang out on, that matters, right? They may not come back. So these types of things add up. It matters in our roads and our infrastructure, slowly eroding the sand beneath or the sand or substrate beneath our buildings, that sort of thing. So we have 25 to 40 days in 2050. By 2070, we expect to have water levels in that range, about 100 to 200 days per year. And that's when you start to get to the situation, I don't know if you heard the term in some of the news stories that were out there, of the new normal. So it's no longer really an event anymore. It's just kind of what we expect. And at that point, hopefully, we will have worked on our infrastructure and changed, and we won't be actually seeing that much flooding in our roads that many days per year. But it will take some investment between now and then to keep this from happening 100 to 200 times a year. And what does that do for our beaches? We're going to have to spend a lot of money on renourishing and figuring out how to make that sand stay where it's supposed to stay, or so to speak. And just a little tidbit here for anybody who's wondering, how likely is it that we could actually melt enough ice to raise sea level by a meter or 3 feet, a little more than 3 feet by 2100? So can we really affect our planet that much? And honestly, you're not affecting it that much. The amount of water stored on the Greenland and Antarctic ice sheets is equivalent to about 62 meters of sea level. So it's not like we have to warm the planet to the point where we melt all the ice that we have in order to see real change on our coastlines in terms of sea level rise. We have to melt less than 2% of it. Right? If all we melt is about 1.6% of the ice on Greenland and Antarctica will see this much sea level rise and have this type of 200-day per year effect. So it's really not, it's not like you need to be one of those people who's like, oh, climate change is going to like just melt all the ice on Earth and we're going to go back to prehistoric ages with the dinosaurs. A small amount of warming can have big impacts on our lives and our communities. So I'll end here just by putting up a few links here that you might be interested in based on this talk. And I was maybe going to I probably won't have time for that. I was going to click on a couple of them and show you, but I won't. I'll just put this up at the end if you want to take a photo of it or copy a couple of them down. But so at the U8 Sea Level Center, we have a seasonal sea level forecast product that's we recently started putting out this summer that you might be interested in. And here's a link for it here. And basically, that's where we're actually looking at models, and also we're planning on incorporating some of the stuff that I showed you before, like for the rest of the summer. Those kinds of things. We also have tide predictions there, so you can get an idea of what the sea level is going to be, or at least in a forecast sense, for the next few months or so. There's also this really nice product by PAC-IUS, and what they do is it's only looking a week out, but what they do provide is they add the wave part on top of it, because once the swell is generated somewhere in the Pacific, you can pretty much predict when it's going to hit us, right? So what they do is they add the wave part on top of it, and so they have a wave run-up or wave setup forecast that includes a short projection of sea level, and then they add the wave part on top of it. So that's really interesting to look at too for the next week or so. Like for instance, when we get to these times, that would be a really interesting thing to look at to see if we're going to get some impacts there. The last thing I wanted to point out is the UH Sea Grant King Tides project, and I think Mahealani told me that they gave a talk not too long ago here, and that's a really cool project, and it's a really great way for us as scientists to connect what we're doing to the impacts that are actually happening in our communities. Because if you're not familiar with it, or if you missed their talk, then basically it's a website, and I think there's an app as well, where you can go, and if you observe high water levels or flooding during one of these events, you can take a picture and upload it to their website or through their app, and they will geotag these things and associate them with particular high water level events, so that we can go back and say, okay, we're predicting sea level to be this high, and these are the predicted impacts in this place, and this place, because we have pictures. We know what that's going to look like for this particular water level. So that's a really cool project, and I would encourage you to participate in that if you can. Okay, so just a couple of conclusions here, and then I'll stop and we can have some questions and answers and that sort of thing. Basically, king tides, the definition is the 2 to 3 highest astronomical tidal heights per year. So that does not necessarily mean the highest water levels. So when they talk about king tides in the news, I don't know if they're getting it right or not. The king tides are the astronomical piece. That's the sun, moon, earth part. What we saw recently was partially due to high tide, but mostly it was due to a combination of a lot of things. And it was due not only to tides, but to sea level rise in the long term. We saw that. We saw the El Nino piece of it and how that added on. We also saw the eddies. And then we talked about the wave part on top of that as well. So it's really a confluence of a lot of different factors that led to that coastal flooding, and that's the way we need to approach this problem going forward. And so, like I said, at the end there, while mostly this falls in the nuisance category, we're not losing our homes and we don't have FEMA in our backyard or whatever because of these types of events, but they will become increasingly problematic as we go forward, as they become more and more frequent, and we will have to deal with that problem. So that's where I'll stop. Thank you.
Questions?
Yeah, one thing you didn't mention, which I gather is not part of what you're doing, is the groundwater.
Yep. So that's a whole other. Yeah. So the question was mentioning the groundwater, and I actually had a couple of slides that I was going to put in there, but it just ran out of space. So that's a big part of it. And actually, I didn't mention it, but when we talk about this flooding in the road like this, That's not because you have like water coming in from Kaimana Beach and up over the grass and over here. This is actually water coming up from below. It's backing up out of our drainage systems and things like that. So, and the groundwater is a piece of that as well. So when you get high water level around the island, it pushes the groundwater out from under us and pushes it out into the surface and can flood our streets and parking lots and things like that.
In general, when did the El Nino start, and when is the next La Nina?
That's an excellent question, and a lot of people are working on that. So this last El Nino event was really weird, because I don't know if you remember back in 2014, everybody was like, oh, the El Nino is coming. And it was like, man, this was going to be the big one. It was the big El Nino was getting ready to happen in 2014. And then it kind of started, and then it hiccuped, and then it kind of just died. And nobody really understood why. It sort of persisted a little bit, and then in 2015, it started up again. And so it was kind of this weird, like slow, meandering El Nino that kind of peaked. It did peak at the end of 2015, but it was still a weird event. It was very northern hemisphere centric. So usually El Nino events are kind of like equal south and north of the equator. But this one wasn't. It was very northern hemisphere centric, and I think there's going to be a lot of interesting analyses and studies going forward on this past El Nino. In terms of the next La Nina, you might have to wait a while, because right after this El Nino event ended, they were initially forecasting to have some very minor La Nina conditions, and I think we had very weak La Nina conditions for like a few months. But then we started going back into moderate El Nino conditions. So there's really no telling when. It's really a weird event, and we can talk about this for a while, because there's another thing called the Pacific Decadal Oscillation, which is kind of like really long-term, decades-long El Nino. Essentially, it's smaller, but it's kind of like this much more slow sort of process. So we're currently investigating kind of what is the interplay there. So are we seeing a phase change in the Pacific Decadal Oscillation, which will bring us more, so our baseline will be more El Nino-like for the next 10 years or so. And I think that's kind of where we're headed. You back there?
Sorry.
Was this event predicted? The eddies, the beginning, the minor water elevations. Was that predicted? And did you see it previously with other
The last part I'll get to in a second. That's an excellent question. For the prediction question, we weren't really on top of it. It hadn't been an issue. So we were kind of looking at, so this piece here, where we were, and seeing this kind of stuff happen, and we sort of saw this blobby stuff kind of out in the middle of the Pacific, but weren't really thinking about how that might actually interact with all the other factors that we had lining up at once to create that type of event. So no, we didn't really predict it, but we've actually, because of that event, we've put a lot of effort, I think, into creating some tools that hopefully we will be able to predict that event going forward. The National Weather Service actually issued its very first ever coastal flood warning that was not associated with a storm, at least for Hawaii. So they are now on this as well because of that event, and they are going to start monitoring these things and looking at our tools as well as their own to figure out when there could be coastal flooding events for these same types of processes. Oh, and the last part of your question was other El Ninos. So interestingly, the biggest El Nino we've ever seen was the 97-98 event, and we didn't get this. And that's something we're really trying to figure out, and we think it has to do with the fact. So there's a lot of interesting wind kind of features and structures over this region between Mexico and Hawaii. And there are certain types the way the winds can blow, in particular how the wind curl, if you know what I'm talking about. If you have cyclonic natures in the wind, or cyclonic features in the wind, that can actually cause a negative sea level anomaly. So that can cancel out the El Nino part, potentially. So that's kind of the avenue we're looking at. We're going to try to figure that out. Why was it? So if we're seeing this so clearly with this El Nino event, why didn't we see it with the previous big El Nino event? So we're kind of working on that problem.
Do you, besides the tide fronting, do you monitor the wave heights? And are the wave heights measuring higher as well?
We have buoys that measure the wave heights. They're not necessarily our buoys, but Pekayus has a big network of buoys around the island. But in order to actually get the, I'm going the wrong way here. The water level itself at the shoreline from the waves, you have to, so we have a couple of different places, and we're doing this all around the Pacific, where we're putting pressure sensors out on the reef so that we can actually relate the amount of wave energy you're getting at the reef edge to the actual amount of water level change. And so we do have some sensors. They're just pressure sensors that are sitting out in various places in Waikiki. That's on the North Shore. We have these in different islands around the Pacific, trying to get a handle on how much swell creates how much water level change. But it's a tough problem because it's different everywhere, because it matters what the roughness of your reef, it matters the shape of your reef. If there's a big channel nearby, then you're not going to have this effect very much, because what's going to happen is you're going to set up that big shoreline water level, but then it's just going to leak right back out the channel. So it matters locally what your reef looks like, and we're going to be running some models in Waikiki to try to assess exactly how that's going to look.
What are your sources of information? Where do they all come from? NOAA?
That's a good question. So NOAA has a lot of, so NOAA runs the tide gauge that's here in Honolulu. So that's one source of the information I showed here. There's various international cooperation that goes into getting the sea level from satellites. So NASA and NOAA and the European space agencies all work together. All work together to get those satellites, keep those satellites going, funded, and get the data, process it, and give it back to us in a product that we can use.
So is this cutback going to affect anything that you're doing?
That's a good question also. So NASA has these satellites going. Right now, there's actually redundant satellites. We have more than one. One of them is sort of ending its life. The other one was just launched within the last year or two. So, and each satellite has redundant instruments on it. So because it was just launched, these things have lifespans of 10, 15 years or so. We should be good with the satellite sea level measurements. There are also other really important climate observations from space that are a little more in danger because they're not actually flying yet. There are some instruments we have that are designed, ready to go, but there's doubt on whether or not they're going to get launched, right? Because of the current funding climate. So we'll see. We'll have to see what happens, but we should be good for sea level.
In the many years we've been looking at the Honolulu tide records, the predicted versus the observed.
Yeah.
I don't recall seeing many negative anomalies. Is that just bias because it's not causing problems, or is it?
Oh, so you mean like what is it?
Below predicted tide level.
Oh, okay.
Yeah,
Right. So when they do the predicted tides, it's actually, so the National Ocean Service defines various datums. And the one that I've used here, and I think the one that's probably used most often when you see those tide charts, is mean lower low water. So it's the average, you know what that is. So that was defined, though, that the current epoch for the definition is 83 to 2001. So I think that's probably why, because we were defining that epoch from 83 to 2001, but we've had additional sea level rise and mostly sea level rise since that time, and so that's actually going to affect whether or not you get negative values.
One other corollary to that, do these El Nino spin-offs or oscillations, will that get factored into what we calculate as the sea level rise in Honolulu, or will it get filtered out as in the region? So
when we calculate a trend, we try to account for that type of stuff, right? So a lot of times when we calculate a trend, what we'll do is there's a certain index for El Nino, and there's various ones, and so we treat that index and sort of a sine cosine sort of partner with that index to try to take out as much of that variability as we can before we calculate the trend. Because if you have an endpoint that's really high, it's going to bias your trend high. So we try to remove that variability before we calculate the trend. Does that answer your question?
So these eddies, what's keeping them stable exactly? Is it just a pocket of warm water, or is there a rotational component?
Yeah, there's rotational components. So it's kind of like a hurricane, essentially. Like a hurricane has a low center, and because of the Coriolis force and the fact that we're on a rotating planet again, you have a low center, so air tries to rush in, but it gets deflected to the right in the northern hemisphere, and you get counterclockwise spin around the low center for the hurricane. It's the exact same thing in the ocean, where cold water is a low pressure, and warm water is a high pressure, essentially, analogous to the atmosphere.
And will they go all the way across the Pacific, or how long will they hold together?
Well, it's kind of hard to keep track of because they kind of merge and blend, and every time they hit an island, they can have a new eddy spin off and cancel it, or there are algorithms out there that will track eddies, and I actually have not sat there and said, okay, will this eddy get to the other side of the ocean? So I don't know. That's a good question. But they do hold together pretty well, but they do interact a lot, and so that's why it's hard to keep track of just one eddy.
Some of the tide records, we look at the offset, predicted minus, measured minus predicted. There's also a cycle, a 12-hour cycle, and do the difference. And there'll be difference will be greater towards a higher tide and smaller towards a lower tide. You know what I'm talking about? Have you seen that?
I can imagine that's probably true, because the way that we get predicted tides is essentially a fit. So because these things are deterministic, what we do is we take the entire record, or at least there are different ways of doing it. You can either look at the entire record, or you can look at it in kind of running overlapping chunks. But you have to fit these things. So you're not actually, because the ocean is very complicated, and it's not as simple as two high tide bulges on the Earth, and then there's low tide areas, and then because the land gets in the way. So the water can't just follow the moon around. So what happens is that it's very complicated, and you can't really run a model that will get it perfectly. So what we do is we take all the different harmonics, we know what the frequencies should be, and so we fit them, and then we minimize the differences to get a prediction. So essentially you have a bunch of different sine curves that all have a different frequency corresponding to particular tidal frequencies. And then we fit those to the data. So it's so they're not perfect fits, is all I'm trying to say. They're not perfect fits. They're very close, but they're not perfect. So it's not surprising that you would see a little bit of difference, because you can't get it perfect.
I'm talking about a residual between a periodicity and residual. Right.
So what I'm
pretty large.
So what I'm saying is one of the fits to one of those harmonics is not good. If that's the problem. Do you know which tide gauge it was? Was it Honolulu? Or?
And what these the anomalies, I think super elevation.
Yes,
so there's less at low tide than at high tide.
Not perfect. It's not perfectly in phase, but it has the same period.
Yeah, it doesn't surprise me that it's a little bit off, but if it's really bad, we should have a look at it. I mean, it's really off in terms of is it the amplitude or the timing that's off?
Well, there's not the phases. It's not completely in phase, but it's what I'm looking at is the amplitude, and it's not really predicted. It's an amplitude variation in residuals.
And it's is it daily, or what's the frequency?
As I say, it'll come and go, and it's when you look at these records over time, you'll see a week, for example, there will be a periodicity residual.
And then it goes away?
And then it goes away.
Okay, so that
I've also seen it, just to say, I've seen it increase towards Kauai. Kauai will have a definite periodicity that's missing in Honolulu.
Oh, well, okay. So maybe we should talk more after. I feel like we're getting down in the weeds here. Does anyone have any other questions?
Forgive me because I don't know how to pose my question, but I noticed in here around 1990, you see one of the lowest parts of the sea levels. And it was around Finiki's time. And how does, say, you hit all of this and it forms the perfect storm for what you're saying, you got either a currently, everything. And there's a hurricane that comes, would that be even more catastrophic then? I mean,
So if we have a direct hit from a large hurricane, this stuff is, it's just mini-me, right? It's like, it's not going to matter that much. If you look at like pictures of like Hurricane Sandy or something, and you have like wave heights and water levels splashing above piers and things like that, I mean, that kind of direct hit from a hurricane is going to swamp anything that we're talking about here. So
I noticed when, as I lived on the ocean back then,
Mhm.
I noticed, the waves were not big at all, but the speed of the waves, they're small, but the speed kept pushing faster and faster, which flooded the areas, the land, even in Hawaii, right here over on Fort Lock. So that's why I wondered if the tide being higher would have made it even, would have impacted it even more.
certainly if a storm hits at high tide, it's going to be worse than if it hits at low tide, because tides actually have a very big range. The stuff that we're talking about here with like eddies and like that kind of stuff, we're talking about centimeters or inches, that kind of thing. But tidal range is huge, so it makes a big difference. We saw like at the beginning, right? We had -1 to 3 feet in that range of that record going back to 1905. So if we have a storm that hits a low tide, it's going to be 4 feet lower storm surge than if it hits at high tide, right? Or potentially. So that the tide could definitely make a big difference there.